Hello everyone, my name is Sympathy, and for today I'm going to be teaching Foundation 1, Binary, Denary, and Hexadecimals for the field of computer science. Now before we begin, I just want to give a bit of information that all timestamps will be available on the timestamp of this video as well as the description. So if you guys want to skip forward to some parts, then go ahead. Now since this is my first learned video, I figured you guys might be wondering who the hell am I to teach computer science. So let me introduce myself quite briefly. Hi, my name is Timothy William Ibowo. I am an 11th grader in Sekolah Buguraya. The few here are some of my achievements, some of my feats that I've achieved in computer science. I have achieved an A star in the computer science at GCSE curriculum. I have above 5 years of experience in computer programming, although not competitive, but I understand the basics. I attained gold medal in informatics at Pesona 2025, as well as a gold medal in informatics at Competition Science Indonesia 2025. Okay, so now let's begin with what we're going to learn today. So we are going to be covering the definitions and characteristics of binary, denary, and hexadecimals, as well as how to convert between one another. Okay, so let's start with definitions first. Starting with binary. So binaries are basically numbers that consist of zeros and ones, and it uses a base 2 system. And when it says base 2 system here, it means that it has two digits that it uses, zeros and ones. And then it's commonly in 8-bit form. 8-bit here means it uses 8 digits. So let's say 0110, 0110, that's 8 digits. But then it doesn't have to be an 8-digit. It's not limited to 8 digits only. It's just commonly in 8-bit form. And then it also has a weight factor of 2 to the power of n, which I will explain later. Okay, so now let's play a little game. Let's identify whether these are binary or not binary. So the first one here, if you guys notice, if you guys analyze quite briefly, of course it is binary because it contains only zeros and ones, and it's also in the appropriate format. However, the second one here, as you guys can see, since there's a 2, therefore it's not binary. How about the third one here? It only has 4 digits. Is it still binary? The answer is yes, because as I said before, binary does not have to be limited to 8 digits. It can also be 4, it can be 3, 2, or even 1. That's still binary. Okay, so now let's talk about the weight factor of binary itself. So as you guys can see in the previous slide, there are 8 digits commonly in binary, and each of these digits hold a certain weight factor, and this weight factor determines how many bits does the digit store, which also determines the storage size, the storage of the binary itself. But let's not get too deep there. All you guys need to know is that each binary digit has a weight factor, and it begins from the far right here, as you guys can see on my cursor. It begins with 2 to the power of 0 here, where as I said before, weight factor is 2 to the power of n. N represents the current digit. So since this is the first position, in computer science, we always start with 0 instead of 1. So in here, it's 2 to the power of 0. And we know 2 to the power of 0 is 1. So the first digit will hold a weight factor of 1. And then going to the left here, we have 2 to the power of 1. And that holds a weight factor of 2. And continuing to the left, it's always going to be 2 to the power of n. So in here, it's going to be 2 to the power of 2, which is 4, 8, 16, 32, 64, up until 128 if it is 8 digits. If it continues, then it's going to be 2 to the power of 8, which is 256, 512 for the 10th digit, and so on. So that's what weight factor is, and it will be extremely crucial, especially when understanding conversions between binary and denary. So make sure you guys keep this in note. Okay, so now let's learn about denary. So denary is pretty much numbers that consist of digits 0 to 9. So just think of your regular math numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's all denary. That's why it uses a base 10 system. Be careful, it's not base 9, it's base 10, because 0 is also a digit. So if you count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, that's 10 digits. And if we are using a binary in 8-bit form, the denary value is usually between 0 to 255, and I will explain why later. Okay. So now, before we get to hexadecimals, let us learn about the conversions between binary and denary. And this uses the principles of weight factors. So, we have a binary value here, 0100, 1101. So let's convert the following binary sequence into denary. So if we want to convert this into denary, we have to bring up our trusty old weight factor. So it is extremely crucial if you guys draw this weight factor table, as it will be used a lot, like a lot, in binary-denary conversions. So after you guys draw this, this is what you guys have to do next. Step 2 is compare and store. So what I mean by this is if the binary digit is 0, then you have to ignore it. If it's 1, then you store it. Okay, so you guys may be really confused by what that means. So let's give an example here, a visual illustration. So if you want to convert from binary to denary, you can start anywhere, honestly, but I like starting from the left. So in here, as you guys can see, we have the number 0 as the digit of the binary, and since it's 0, then we have to ignore it, so we can just ignore that. Now we have the number 1, and if it's 1, then we store. So we store the weight factor of 64. So basically, if it's 1, you have to store the weight factor itself. So the weight factor here is 64, so you store it 64. Now the next one is 0, so we can just ignore it, and the next one is also 0. Next one here is 1, so therefore you store the weight factor of 8 here. And the next one is also 1, so you store 4. This one's 0, so you ignore. And the last one is 1, so you store the 1. So now you have these 4 digits. And what do you exactly do with them? That's where the third step comes in. This is where we sum up all of the stored numbers. So after we have all of the numbers, we just need to sum it up. And then there's your result. So the binary digit of, the binary digit of 01001101 will result in a denary of 77. So that's pretty much how you convert binary to denary. Okay, so now let's do the opposite. Let's convert denary to binary. So although it's different conversion, however, you still have to use the trusty old weight factor. Okay, but instead this time we have to do the opposite process, and I'll show you guys how to do it here. So after you guys draw the weight factor table, you guys have to compare and subtract. So if the denary is more than or equal to the weight factor, then subtract. And if the weight factor is more than the denary, then simply ignore. So as you guys can see here, we have the denary 216. Okay, and for weight factor, you always have to, for binary denary, you always have to start from the left. Okay, so here we have 216, and we're gonna compare it with 128 here. So we see here that the denary is more than 128, and therefore we have to subtract. So if you subtract those, it becomes 88. After we have the denary value 88, we bring it up here again, and then we compare it with 64. So is 88 greater than 64? The answer is yes. So therefore, you subtract it. You get 24. Now you bring it up, and now it's 24 and 32. Now it can't be subtracted, so we can just ignore it. See? So now we bring the 24 again to 16. And this we can subtract, so it becomes 8. And you repeat the process until you reach the point where you reach the point where both of the values are going to equalize, like this, 8 and 8. If it equalizes, then we still use the rule. If denary is greater than or equal to weight factor, subtract. Since this is equal to, we subtract it, and it becomes 0. So obviously, the rest is also going to be 0. Now, what do we do with this? This is where the third step comes in. That is where we identify. So if you're able to subtract, then you have to mark it as 1. And otherwise, you mark it as 0. So if we pay attention to the first digit here, we're able to subtract 216 by 128, and therefore we mark it as 1. The next one you can also subtract, so we mark it as 1 as well. Now the next digit, however, we can't subtract it, so therefore we add a 0, and then continue this until the entire binary value. And after doing all of that, we have just converted denary to binary. This is our binary value now. 1101 1000. Ta-da! It's that easy. Okay, later we'll try to practice that after this. So let's just move on first to hexadecimals. So what are hexadecimals? Hexadecimals, in contrast to denary, they not only consist of 0 to 9, but they also have A to F. And because of this, it has a base 16 system. Because 0 to 9 is 10, and A to F is 6. So 10 plus 6 is 16. That's why it's a base 16. And if we assume that the binary is an 8-bit form, which it usually is, then hexadecimal is usually 2 characters long. And we'll see after this. Let's try to play another game. Let's try to identify if these are hexadecimal or not. Okay, so let's see this. The first one we have is A4. And since it follows the criteria of consisting of 0 to 9 and A to F, therefore it is hexadecimal. Okay, now we have G9 here. And you guys might think this is, fine, but it actually is not hexadecimal because it does not follow the property of A to F. G is beyond that scope. Henceforth, it's not hexadecimal. Okay, next is 2, 5. Now, although you guys may think it's, a form of denary and not hexadecimal, but it is also a part of hexadecimal since it follows the criteria of consists of 0 to 9. Now, how about 0 and 0? Since it follows the scope of 0 to 9, then it is also hexadecimal. Okay, so this is an extremely useful concept that you guys should know. So hexadecimals, in contrast to binary and denary, is probably the most seen by us in real life, and that's because it's the most applicable. And this is because it holds a lot of unique values in contrast to binary that only holds zeros and ones and denary that only holds 0 to 9. Hexadecimals also holds A to F, and therefore it allows for more unique values. So some examples of hexadecimals around us include MAC address. So as you guys can see here, this is a MAC address. It has 12 hexadecimal values. And then next we have hex codes, which has 6 hexadecimal values, and also URLs sometimes. So these are things that you guys should keep a note of. Hexadecimals is everywhere, and you guys use it without even realizing it. So yeah. So now let's learn about the binary hexadecimal conversion. Now this is a bit more complicated and more time consuming in contrast to binary-denary conversions. So let's break down on how I would do it. This is the step that I found most efficient, although it takes memorizing. So first of all, you have to pick a side, which one's binary and which one's hexadecimal. You're sort of making a table here, so you guys can put labels. And then next, let's begin with the binary. So the way you want to order the binary is starting from 0, 0, 0, 0. That is the lowest possible binary number. Okay, 0, 0, 0, 0 is absolute lowest. It's 0. It's the lowest binary value. And if the binary is 0, the hexadecimal also should be 0. Okay, makes sense? Now, let's move on to the next binary. What would you guys think the next binary is? The way the binary works is that we're going in increasing order. So from the lowest to the highest. So therefore, the next binary should be 0, 0, 0, 1. Okay, and because of that, the hexadecimal is also 1. Now here's where it starts to get trippy. Because since binary uses a base 2 system, it does not have a 2. So instead of going 0, 0, 0, 2, it actually goes 0, 0, 1, 0. And the reason why is because you can't do anything else with the first digit here. You can't increment it again by 1. You can't make it 0, 0, 0, 2. So you have to involve another digit, and that's the next digit to the left. Therefore, the next highest possible digit is 0, 0, 10. Think about counting, but you can't use the digits 2 to 9. You can only use 0 and 1. So after 0, 0, 0, 1, the next possible digit is 0, 0, 1, 0. But the hexadecimal itself will still be 2. Okay. Now you keep going with this. The next digit will be 0, 0, 1, 1, and the hexadecimal will be 3. Okay. And you go on until the highest possible value is 1, 1, 1, 1, and the hexadecimal should be F. Okay, the table should look like this. So as you guys can notice, the binary, it starts from 0, 0, 0, 0, and the hexadecimal itself is 0. And it goes all the way to F. Now, if you guys notice here at 1, 0, 0, 1, the hexadecimal is 9. And then the next hexadecimal value should be A. Since there's no 10, the next value after 9 is A. So we start with the numbers, and then we go to the letters. So after 1, 0, 0, 1, it goes to 1, 0, 1, 0, and that is A. And then we continue with 1, 0, 1, 1, that's B, so on until 1, 1, 1, 1, and that's F. Okay, so what exactly do we do with that table? Why do we even need to memorize it? And that's because it's extremely crucial for the binary hexadecimal conversion, this part, the splitting part. So if you guys notice, each hexadecimal holds 4 digits of binary. For example, the hexadecimal of 3 holds 0, 0, 1, 1. That's 4 digits. Therefore, if we have an 8-digit binary number, that means it should hold 2 digits of hexadecimal. If, let's say, you have 12 digits of binary, then it should hold 3 digits of hexadecimal, and so on. That's the logic. So I'm sure you guys can guess now. If we want to convert from binary to hexadecimal, we have to first split the binary into 2, like this. So you get 0 1 0 0 and 1 1 0 1. And then I'm sure you guys know where it goes from here. You have to identify each of the binary according to the table to get the hexadecimal. So if we pull up the table here, so let's identify 0 1 0 0. What is the hexadecimal here? So we look at here, this row right here, and we see that the hexadecimal is a 4. So therefore it starts with a 4, and the 1101 is this one. It's a D. So the hexadecimal is 4D. And it's extremely important to not switch up the order. So if you guys notice, the binary starts from 0 1 0 0 and 1 1 0 1. So the hexadecimal should start with the hexadecimal of 0 1 0 0, and that is 4. So make sure you don't start with D, because 4D and D4 are completely different hexadecimals. Okay, so how about hexadecimal to binary conversion? So it's pretty much doing the exact same process backwards. So you have to convert each hexadecimal to binary, then combine both binary values together. So with this, you have to bring the good old table again. So this is a table, as you guys can see right here. So if we, let's say, have the hexadecimal of 2A, 2 is 0 0 1 0, and A is 1 0 1 0. So if you combine it together, it becomes 0 0 1 0 1 0 1 0. Okay, so that's simple. How about hexadecimal to denary, or denary to hexadecimal? That's where it gets a bit complicated, because there's no straight path to converting from denary to hexadecimal and vice versa. So you have to convert denary to binary first, and then to hexadecimal, and vice versa. Okay, that should cover the entire topic of conversions. So that is all for the material itself. Now after this, we're going to be continuing with the practice. Let's do some sample questions from our practice. Okay, so here we have a worksheet here about binary, denary, and hexadecimals, and this is already outside the material. So if you guys want to just skip this part, then it's okay. So thank you for watching. But if you guys still want to learn more about how to convert binary, hexadecimal, and denary, then you guys can watch this practice. Okay, so let's see the first question here. So we have to outline two differences in the characteristics of binary and denary. So you guys also have to take note that not all questions are about conversions. There are also some about theory. So two differences here. We can also refer back to the presentation that I gave you guys. So the first thing I think of is, of course, binary only has 2 digits and denary has 10 digits. And it's extremely crucial that in computer science you use the appropriate keywords. So instead of saying 10 digits, 2 digits, you say 2 bits and 10 bits. So let me write that down first. Okay, and after that, another characteristic I would think about is, it's actually quite simple, correlating with digits. Binary only has 0s and 1s, and denary has 0 to 9. Now you guys might think, isn't that the same as 2 bits and 10 bits? And the answer is no, because in 2 bits and 10 bits, we're only mentioning how many digits there are, not the number itself. So we can put that down. Okay, as so. So that itself already answers the question. And I think it's also really crucial that you guys see how many marks there are, because that tells you, how many answers or how specific you need to answer it. So if it's 2 marks, you only need to outline. Okay, you only need to state it. So nothing much. Another answer would possibly be about its application itself. So you could say denary is used for IP addresses, binary is used for whatever, something else. Or binary can be read by computers, denary cannot. So those are some other options that you guys can answer. In the end, it all depends on what you want to answer, so long as it is true and factual. Okay? So this is what I would answer. Okay, next we have a conversion here. Convert the following binary sequences to denary. We only have 1, so it's fine. We have 0, 0, 1, 1, 0, 1, 1, 0. And when we have this, we want to pull up our good old, what's the name? The weight factor table. Yeah. Okay, so I would draw the weight factor table first. So let's draw that. Okay, and then after that, I would put this digit down here. Or we could do it directly if you're fine with that. So the first digit is 0, so this we can ignore. The second digit is 0, so with this we can also ignore. The next one is 1, so we store it, so we bring this down, 32. Next is 1, so we store it, 16. And then 0, we ignore the 8. 4, since this is 1, so we store the 4. Next is also 1, so we store the 2. And then this one's 0, so we ignore it. So now we have all of our stored digits, and we just need to add it up. And this becomes 6 plus 16, 22, plus 32 is 54. And that's our denary. So you guys can, slow down and pause for a bit. But of course, since if you're doing this in an exam style condition or even in a competition or something else, then you have to be quick. So so this is probably the process that you guys should write. Since this is 2 marks, so you also need to have some process marks. Okay, next up, convert the following denary sequences into hexadecimal. So we have the 89 here, and we have to convert it into hexadecimal. This is 3 marks, and the reason why it's 3 marks is probably because we have to convert it to binary first and then hexadecimal. So technically, there's 2 conversions. So let's convert this into binary first by doing the weight factor table. Okay, so let's draw it again. Okay, so let's do this directly. Let's be quick. So 89 and 128, it cannot be subtracted, so it's 0 since it can't be subtracted. Next, 89 and 64, it can be subtracted, so it's 1. And that leaves us with, how much is that? 25. 25 cannot be subtracted by 32, so it's 0, so we bring it to 16. 25 and 16, we can subtract it, so it's a 1, and that gives us 9. 9 and 8 can also be subtracted, so it's also 1, and that gives us 1. 1 and 4 cannot, 1 and 2 cannot, and 1 and 1 here can be subtracted, so it's 1. So this is our binary value here. We have 0, 1, 0, 1, 1, 0, 0, 1. Okay? Now with this, we can convert it to hexadecimal by using the table. Now, this takes up a lot of time, drawing the table. So I'd say just draw the table once. You don't need to do it in here. You can do it, let's say, in your scrap paper or somewhere else in the paper. But you should also apply it to other questions. So you'll see what I mean when I say that. So let me just write down the table. Starts from 0, 0, 0. Okay, here we go. This is the table, which ironically it gets smaller the further it goes down, but it's fine. So we have 0, 1, 0, 1 here. So we look at 0, 1, 0, 1, and that's here. So it's a 5. So this is 5, and this 1, 0, 0, 1 is this one, which is a 9. So we put 9 here. So therefore, 89 into hexadecimal is 59. That's our answer. Okay, after we're done with that, let's move on to the next question. So, okay, this is interesting. So you guys should also consider that not all the questions are going to be as straightforward as this. Convert the following blah 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 into blah blah blah. There are some questions that's definitely gonna make you have to read. Okay, and you guys also have to be good at digesting this. So let's read the question. A student wants to add 2 hexadecimal values, and to do so, the student follows a set of instructions listed below. 1. Convert both hexadecimals into denary. 2. Add the denary values, and 3. Convert the result back to hexadecimal. Okay, this is quite annoying because if you count, there's gonna be 4 conversions for each hexadecimal. So from hexadecimal to binary to denary, and from denary to binary to hexadecimal. That's okay. Let's do this step by step. So we have 2 hexadecimals here. Okay, so the first step that we have to do, it's actually quite simple. We just need to follow the instructions. Okay, if you follow the instructions, you're fine. So we have to convert them both to denary values. So the first step that you guys should do is you guys should convert it first to denary values. So of course you guys are gonna convert A1 first to binary and then denary, as well as 3B. Okay, if you guys convert it, you guys should get the denary 161 and 59. Since I don't have enough time, I simply Googled. But don't follow me, practice. Okay, and then after we get this, what's the next step? The next step is we have to add the denary values. So of course we have to add this. 161 plus 59. How much is that? That equates to 220. Yeah, 220. Sorry, it's really late here. I'm really sleepy. Okay, 220. And then what's next? After that, we have to convert the result back to hexadecimal. So now we have to convert this back to hexadecimal. And how much do you get? Let's Google. Okay, and if you convert this, you will get the hexadecimal of DC. That is the final answer. Now remember, when you're doing questions like this, you always have to look at the marks. And here there's 4 marks, and therefore you have to put process, okay? So you can't just do what I did. I simply wrote the denary immediately and then converted back immediately. I didn't put any conversion processes. So you guys have to make sure you guys also put your process, or else you guys won't attain full marks. But this is the step on how you do it. So every time you do questions like these, you always have to break it down one by one to make sure that you get the point and the gist of the question itself. Okay. And with that, you guys have completely, successfully mastered the art of binary, denary, and hexadecimal. So, congratulations, good job. You guys are doing really well. I hope this has been a very informative video. But yeah, that's all from me. So thank you so much for watching, and I hope you guys learned something new, and I hope you guys gain a lot of knowledge from LearnIt. So yeah, thank you.